Okay, I think I hit the record button. All right, so this week I chose four problems here, and the problems are all, I guess, some kind of a search. They are continuation of last week's ideas, but some of them are a little bit more advanced. So I want to show you the problems. I want to show you how I solved them. Um, Let me see how it's okay. And then maybe for the first problem, I'm going to put Julie on the spot since she did it. So let's look at the problem. Okay, so flip five. There's a logic puzzle in which you have a square grid of 3 by 3 cells. Each cell is either black or white initially. And when you click on a square, it flips, toggles the color of that square and the colors of its four immediate north, south, east, and west neighbors, uh, assuming that they exist, of course. The problem is to find the minimum number of cells the number of cells clicks that transforms the grid to all white into the input grid. Uh, you cannot rotate the grid, blah, blah, blah. Okay. So the input, um, it's up to 50, which is the number of problems to solve. And for each of the P problems, you get a 3 by 3 initial square, the initial grid, and you have to figure out for each input grid what is the minimum number of clicks you need to transform it all to all white. So the input looks, for example, like this. Star means a black, dot means a white, and you have to turn them all to white. So I don't know if some of you have already seen this game, this puzzle separately from the programming contest. It's sometimes called Lights Out or maybe other things, and sometimes it's more than the 3 by 3. Sometimes it's a lot bigger than 3 by 3. Um, but anyway, this is 3 by 3. So before I ask Julie to tell us what she did, does anybody have any ideas what to do? Let's see, list of participants. Who else is here? Oh, okay, Jenna is here. Hi, Jenna.
Hello.
Okay, so what to do here?
I did have a friend who wanted to talk about this problem and actually was thinking about how it's similar to Lights Out, but they can't come quite yet. They're right
Okay,
now busy. Otherwise,
okay.
I'd tell
Well,
them to jump in.
it's recorded, so if they want to watch it. Um, anyway, so Julie, I'm gonna put you on the spot now since you're the one that did this problem. What did you do?
I got some help understanding what to do, but I know it's like a dynamic programming problem in the sense that what I did was we bit masked each of the squares so that you know like which one is which in like binary, so that when you input it, you'll code it so that you know the first one is like 1 and the next one's 2 and then 4, but like using bit masking, so you start in one integer value, and then with your dynamic programming you can go through and just kind of test them all through brute forcing it and
Okay,
see. So you keep track of like which boards you visited, so that if you go through them all, you can just check which flips you've done and count them, and that way through dynamic programming you'll keep track of that because it stores all of them in your array.
okay. So you have some kind of system that maybe it's like this. It doesn't matter exactly which one you call 1, 2, 4, but that's kind of what you started with. And maybe you say white is 0 and black is 1. So if you have, let's say the pattern, uh, black here, let's say like this, then you're going to represent this as a binary number 1 plus 4 plus 16 plus 128, whatever that is, right? Is that what you did?
Yep.
Okay, so this is, if I haven't made any mistake, it's 149. All right, and then each one of these, I guess, is called a state of the game, right? So obviously, you have an initial state that they gave you, and then the state that the goal state, it's of course just all 0. So I'll just use the integer representation, which is 0. So you have basically, this is what is called state space search, where basically you have a state, right? So you have a state, and then for each state, there are 9 potential possible moves. Okay, because for each state, you can click any one of these 9 cells, and that will lead you to a next state. Okay, so for example, when you click on this one, this will turn white, this will turn black, and this will turn white. So you can figure out what this is, how these things turn, and it will lead to potentially 9 new states. And each one of these would have potentially 9 new states. Okay. Now, it is not true that you always get 9 new states because, for example, if you click on, let's say, this one, and then the next move, you click on this one again, you just cycle back. Okay, you just cycle back to what you had before. So some of these states, some of these 9 moves leads to states that you might have already seen. Okay, maybe this goes to, I don't know, who knows. It can go in different directions. Okay, but the important thing is to think of this as a graph where the nodes, the vertices of nodes, are the states, and the edges, and then I should say directed edges, are the moves. Okay, so every state, there are exactly 9 edges out, and they may or may not lead to new states. So basically now then you're asking, if you tell me where the initial state is, the sort of original state, and you tell me that you want to find a goal state, so what the goal state is, it's somewhere in this graph, this goal state, the 0 state. Okay, so there might be some path that comes down here. And we want to find the shortest path from the initial state to the goal state. Right? That's basically another way to look at this type of problems. So this is very common when you have some kind of a game, and in this case, it was a single-person game. So sometimes they're puzzles, solitaire games, and so on, where you start with, you have some way of remember what the state of the game is. And the word state basically means that if you are playing this game and you stop somewhere in the middle, so you do a few clicks and now you're here, what you have to remember, so that if you go away and then come back and just recall whatever you remember, you can play the game exactly where you left off, right? So in this case, you only have to remember what the board looks like. You don't have to remember how many turns you have taken. You don't have to remember what was the last move. You don't have to remember any of that. You just have to remember what is your current grid. Okay, in other games, you might have to remember more things. So a good way to think about the state is if you have to suspend your game so that you can go away and pick it up again later, what is the minimum that you have to save so that you can restore the game exactly as if you have never left. Okay, so now, if you have a graph like this, and you're basically looking for shortest path from one node to another, I guess you use the word dynamic programming. But another way to think about it, what is another way to think about it? In this case, breadth first search would do, because all the edges have the same cost. If some moves are more expensive than others, then you might want to use, for example, Dijkstra. Okay, so that's kind of the idea. The other thing that you have to worry about, of course, is how big is this graph? Because if the graph is too big, you might as well forget it, right? If the graph is too big, BFS, it's linear time, big O of n plus m, the number of nodes plus number of edges. you better make sure the graph is not too big. So how big is this graph? How many
With
states
all
are
with
there?
all the possible states, I think
Yeah.
it's 512.
512. And where do you get the
Technically
512 from?
511 if because each one is like 2 to the 9 basically. Because
Right.
each one can be either black or white.
Yeah, so it's 2 to the 9. So if you have a bigger array, bigger grid, then maybe you cannot do this. But for 3 by 3, you can definitely do this because it's only 512. And the number of edges basically is 9 times n. Okay, because every edge, so every single state has 9 edges coming up. So in any case, 512 and 9 times 512 is nothing. So you can just code up a breadth first search, and I want to kind of show you my code. Now, Julie, do you think that your code, your approach is in some way also kind of like breadth first search or some kind of a
Yeah.
graph search?
Actually, when I was first thinking about it, I was thinking like you would breadth first search it, and then I was like talking about it because originally I was thinking, well, similar to the good morning problem from last week, you could save all the states in a graph, but like that microwave problem. But then I was like,
Yeah.
well, that's gonna kind of take too long, kind of be messy.
Mm-hmm. Yeah. So let me show you my code, and then we can discuss if we want it. Okay. So this part is really nothing. I just read in the number of cases, and I just loop through that many times. So the meat is in solve. So solve, first I read the grid, and I store the grid exactly the way that you said, right? So I store the grid exactly the way you said, 1, 2, 4, 1, 2, 4, 8, 16, 32, 64, 128, and 256. So my way is exactly what you just said. So here, I just loop through the 9 elements in the grid. I read in the character. If it's a star, then I basically take the 1, 2, 4, and so on. These are just one left shifted a certain position. So this is one left shifted 0 times 1 times 2, 3, 4, 5, etc. And this is a binary OR, a bitwise OR, so that would just kind of set their appropriate bits because these are just a single bit on binary numbers. Then I do the standard binary standard breadth first search. I have a distance array that says what the distance is, and if it's -1, I have never seen it. I will talk about this array up there later. And then I do the standard breadth first search. I start with the queue. Okay, I push the starting grid. The distance of the starting grid is 0. While the queue is not empty, I pick up the stuff from the front of the queue, and then I look at all the 9 moves, figure out where the next state is, and then if the distance of the next state is less than 0, meaning that I haven't seen it before, then the distance next is equals to distance current plus 1, push it back in the queue, and just keep going. And eventually, I will break out, because I have explored everything that I can explore. Distance 0 is the distance to the 0 state, which is my go state. And the only mystery, I guess, is here, how do I get the next state? So I take currents, the current state, and I do the little hat, and hat in C++ is bitwise exclusive OR. So exclusive OR, you will hopefully remember, these are the, truth table. So if you have A exclusive or B, if B is 0, it just basically copies A, and if B is 1, it flips it. Okay. So basically, I'm using B, whether it's 0 or 1, to decide whether I flip a bit or not. So back to my the array up top. Let me just erase everything. So I have 9 numbers here that somehow represent the 9 number presses. So where do these numbers come from? So I don't know why you erase it and keep erasing it, keep writing it back up. Okay. So this is my grid. And basically I say, okay, if I were to, I don't know, press this one. Let's say I press this one. Which ones are changed? This one, this one, this one, and this one. So one of the moves would change these four things. So the mask, what I want is 4 plus 16 plus 32 plus 256. So that would be 308. And that would be this number. Okay, so I basically figure out, I guess hard code it, what are the masks for every single key presser. So for example, if I press this one, then it'll be these three that changes. So these three that changes is 11, and that's this one. And so if I take this 11, for example, and I do a bitwise exclusive OR with my mask, the effect is that it will flip this bit, and this bit. And with the 308, it will flip these 4 bits here. Okay. So basically what I did is instead of trying to figure out how to write this in code, I'm just, since there are only 9 things, I just figure it out by hand and just hard code it in to make things simpler to code. And that's basically it for this problem. Now, I do want to say something else, but before I say anything else, are there any questions? Okay. Now, this problem, it's doable in this way because there are basically 9 squares. 9 squares, each square can be on or off, so we see that there's only 2 to the 9, there are only 512 possibilities. You can search them all, there's no concern. However, if I tell you that, let's say instead of this is being 3 by 3, where's the 3 by 3 up here? Yeah. So instead of 3 by 3, what if I tell you that is, I don't know, 10 by 10? Or maybe 20 by 20? Or even 100 by 100? Can I do 100? Maybe not. Okay, let's say 10 by 10. Then if you use the same approach, instead of 2 to the 9, you'll be looking at 2 to the 100. And there's no hope. Right? If you see 2 to the 100, you either quit or you try to find a different way. Right? So what if it's 10 by 10? Does anybody have any idea what you might be able to do? And to make the problem maybe a little bit simpler, I will just say, what if I tell you, don't give me the minimum number of clicks. So don't give me the minimum of clicks. Just tell me any sequence of clicks. So in some way, it's a little bit trickier because I'm not just asking you for how many clicks you need. I'm actually asking you which buttons do I click, but I'm also not asking you to minimize either. So I want you to tell me if you can find me any sequence of clicks that will transform it to all zeros, or maybe you say it's not possible. That may be a possibility. Does anybody have any idea how you might try to approach this?
If you're doing a similar approach, could you just split up the board into smaller boards and tackle it that way? Instead of 10 by 10, or is that not?
So you're thinking that if you have a big board, maybe you try to look at the 3 by 3 here, and maybe a 3 by 3 here, and try to locally do something, and hope that somehow you can glue everything together. Is that kind of what you're thinking?
I don't think it would be a good solution, but it's a
Yeah,
possible.
there's also a slight problem that when you try to do something here, make it 0, you might touch something here, which will then affect things here, right? And then when you try to clear this one out, you might have to touch things here, and it will flip these things back to back to black or something like that. They might influence each other. So it might be a little bit tricky. So just to illustrate, if you decide to, let's say, break it into 2 blocks, and you decide to first turn all this to zeros or whites. Okay, so if you turn this all to white, and now maybe this is something like this. I don't know, and you decide to turn this to white by clicking on this. So now, so let's say this like this. So now this becomes 0, this becomes 0, this becomes 0, but then now you affect this one back to 1, and then it's kind of going back and forth. It's not clear if you're ever going to finish or if you're going to run into an infinite loop somehow, because things keeps changing. So this is actually quite advanced, and maybe it's a bit unfair for me to ask you this, but it's advanced in the sense that you probably would never think about it this way until somebody tell you, and may not necessarily that you don't understand what's going on if I tell you. So the first thing to realize, first observation is each button is clicked at most once. It never helps you to click a button more than once. Okay, does that make sense? Because if you click the button twice, then you just turn it back to where you were before. And if you click it 3 times, it's the same as clicking it once. Does that make sense?
Yep.
Okay, so this is the first observation. Oops. Okay, why am I moving this observation? Then the second observation, this one you might need to think a little bit longer, is that this order of button presses do not matter at all. Does not matter. So if you decide to press button 1 and then button 2, that's the same thing as pressing button 2 and button 1. The outcome is exactly the same. Okay, and why is that true? So if you, let's imagine that this is one button here, one button here. So when you press this button, you're going to change basically this one, and this one, and this one. When you press this one, you change this one, and this one, and this one twice. Basically, you are really, when you're pressing buttons, you're basically counting how many times each cell is affected somehow. Okay? Either it's affected by pressing a button there or by pressing a neighboring button. But really, all you are trying to do when you press a bunch of buttons, you're just counting how many times each cell is affected by a button press. And if it's even, then nothing happens. And if it's odd, then it's flipped. Okay, so the order of buttons pressed don't matter at all. Okay, it doesn't matter at all. So basically, you can represent, okay, so a solution can be represented by a 0, 1 vector. So basically you have a vector. How many dimensions there are? The dimension is exactly the number of buttons. Okay, so the first component would be button, let's say button 1, button 2, 3, and so on up to I guess we were saying 10 by 10. So that would be up to button 100. But in general, it could be up to whatever buttons you need. And then the solution is either 0 if you don't press that button, and 1 if you press that button. Okay, it's just a binary vector. Does that make sense? Okay. So now what are these vectors for? Okay. So now you also have, so I guess button and cell are kind of interchangeable. So button, each button, for example, button 1 would affect up to 5 other buttons. Okay, it's itself and the 4 neighbors. And I say up to because some buttons may have may not have all 5 neighbors. I guess let's just say each button affects up to 5 neighbors. So for example, imagine if button, I don't know, 5 affects 5, 6, 7, and I don't know, 12 and 20. I don't know how you label them, but maybe it's like, well, okay, it's probably like 4, 5, 6, and then something else, because you probably have 5, 4, 6, and then something on top, something on the bottom. So anyway, it doesn't matter how you label them, but there are 5 numbers that it affects up to. So what you can do is you can say, you can draw a big matrix. Okay, what is this big matrix? There's 100 on each side. And the I column, it's what button I affects. So what am I trying to write? This is a linear system equations. So for example, if this is button 5 and it affects 4, 5, 6, 12, and 20, you would put 0, 0, 0, 1, 2, 3, 4, 5, 6, and then a bunch of zeros, and then 1 at the 12 position, 1 at the 20 position, and then 0 everywhere else. And then the fifth, so 1, 2, 3, 4, 5. The fifth entry here, if it's 0 or 1, if it's a 1, then when you do the matrix multiplication, it will basically copy, it will add this vector into the final result. Okay, let's backtrack. So each column represents the buttons, the effect of each button. The ith column represents the effect of the ith button. And the rows basically says which of the cells will be flipped when you press that button. If your solution has something like this, let's say if this is your solution, that means you press button 2 and button 5. So you look at button 2, the second column, you look at button 5, add them together, and the answer is, you want this answer to be 0. Now, when I say add, I mean adding mod 2. So when you have 1 plus 1, it's 0. And that's basically binary arithmetic. Okay, so if you have been following all of what I said, and this is a little bit tricky, basically what we're saying is we can form a system of linear equations by looking at the columns, by looking at the button patterns, right? The button patterns, and put it in each column for each button. This is my unknown solution. And my right-hand side of my linear system equation is just zeros. So if you have taken some linear algebra, 1410 and maybe higher, then this is basically solving a system of linear equations, but mod 2. And solving system of linear equations, you can use Gaussian elimination and so on. The only difference between what you know in 1410 and another linear algebra courses and doing things mod 2 is that normally when you try to do a Gaussian elimination, you would say, oh, there's this row has 5 something and this row has 2 something. So to get rid of this, I need to basically multiply, if this is row 1 and this is row 2, then I need to do row 2 minus 2 over 5th times row 1 or something like that to zero this one out. This is our operation. But in When you're in mod 2, you don't have to do any of that because there is no 5, there's no 2. It's either 1 or 0. So if you see 1 and 0, if it's already 0, there's nothing to do. But if it's a 1, what do? Well, you just subtract them. But subtracting and adding are the same. So you can just say row 1 plus row 2, and this will become 0 and so on. And in fact, if you do a bitwise exclusive OR, that's actually addition mod 2. So you can actually turn this into a linear algebra problem with Gauss elimination, and you can solve for any sequence of clicks that can get you to zeros. In fact, anything. This doesn't have, the right-hand side doesn't have to be zeros. It can be anything you want, okay? And then if you really want to know what is the smallest number of clicks you need, you're looking for a solution vector that has the smallest number of ones. And that's a much harder problem, which I'm not going to say much more of. So, of course, what I said is a much harder problem, much different way of thinking about the problem is the one that I gave you. But it's another way to look at this problem that is sometimes useful, especially if you have larger problem. You have different problems that are of a similar type. So sometimes you can think about system of equations, and maybe that can help you solving bigger problems. So if you didn't understand any of that, I suppose it's okay because this is not the problem itself. I'm just telling you something that's a little bit beyond what I gave. Any questions about this? Okay, so I don't know. I hope somebody got a little bit of it anyway, because it is definitely not the easiest thing to think about if you've never seen that. Oops, I think I just crashed my whiteboard. I just crashed my whiteboard. Okay. This is what happens when you use free software sometimes. Okay, so that's that one. Now, if I looked at the scoreboard, the only thing that anybody else have tried, although maybe you have read some other problems but haven't tried, it's D. Now it's Matthew here. Okay, Matthew's not here. So maybe I'll just keep going on B then. Okay, page layout. So you're designing a complicated document. Page layout is important. Newspapers and magazines don't just put a whole bunch of text that covers page from left to right. Listing one article after they put multiple articles in a page at different positions to maximize visual impact. Problem is each story has a certain size and prefer fixed location, and you cannot fit all the stories on a single page. What you would like to do is maximize the amount of space you can fill with the stories you have on a single page. Then later, you fill in the remaining space with pictures and ads. Okay, what are the constraints? Up to 500 cases. Each case begins with N, which is 1 to 20. Those are the N story descriptions. Each story has 4 numbers, the width, the height, X and Y positions. Each story has a shape of a rectangle. X and Y is the location of the top left. Every story will fit within the bounds of the rectangle defined by corners 0, 0, and 1000, 1000. For each test case, output the maximum area of the page that can be covered by the given stories. 2 stories are considered overlapping if the area of the intersection is non-zero. In other words, stories may just touch each other by sharing an edge or a corner. Okay. So you have up to 20 different rectangles, and you want to fit as many of them as possible without actually overlapping. But they tell you exactly where the rectangles have to go. Okay, so you can move these rectangles around. Okay, so you have your big page, 1000, 0, 0, 1000, 1000 here. And then you have different rectangles of stories. So maybe there's a story here, maybe there's a story there, maybe there's a story here, maybe there's a story here, and maybe there's a story here, and so on. And basically what you have to do is you want to maximize the area of the chosen rectangles, but you're not allowed to pick rectangles that overlap, but they can touch. So these two are okay, but you cannot pick these three. Okay, these three up here you cannot pick because they overlap with each other. So that's the question. You have n up to 20 rectangles. So basically you have to ask, well, what is really the solution? Anytime you look at these problems, that maybe at the beginning you don't have somebody that tells you this is a search problem, but if you have any suspicion that this is a search problem, you should ask, what kind of things am I searching? Am I searching for all the different permutations, all the different subsets, combinations, and so on? In this case, you're looking at all possibles. You're looking for a subset of rectangles that don't intersect with each other. So that's what you're looking for. And then out of all those, you want to pick the subset that has the biggest possible total area. So basically then, you want to look at, perhaps the first thing is try all subsets, right? We looked at this idea before last time. Last week, we looked at the try all possible subset by looking at bit mask with binary patterns to represent the bits, to represent the elements in a set. So we might start by saying, okay, what if we try all possible subsets of n things? And then for each subset that you're trying, see if the two, if there are any intersecting rectangles. And if there are, then you cannot use it. Otherwise, you can use it and you try to find the one that has the biggest total area. So if we do that, what is the complexity, right? So how many possible subsets are there? Well, 2 to the n. N is at most 20, so this is, let's say 2 to the 20, which is approximately 1 million, which is not bad. 1 million is not bad. But now the question is, what are you going to do with each of these subsets? Well, with each of these subsets, you're going to look and see if there are any pairs of rectangles that intersect. So how do you know if two pairs of if there's a pair of rectangles that intersect? Well, you have to basically look at, for each subset, you have to look at all pairs of rectangles and then ask rectangles, check for intersection. Okay, checking for intersection, we will talk a little bit about soon, but checking for intersection basically is constant time. But how many pairs of rectangles do you have to check? Well, it's basically n squared, right? It's n choose 2 at most, which is basically big O of n squared. If you want to be more precise, it's more like n squared over 2. But immediately now you have this n squared here. So n squared over 2, let's say it's 200. So you have 1 million subsets. Every subset you might have to do at most 200 steps. It's not as bad because some subsets are smaller, some subsets are bigger. Not every subset will be a full 20 elements, but if you want to do a finer analysis, you will still see that it's actually going to be it's going to be pretty bad. But 200 million, if you're going to just use a rough round like this, it's definitely way too big. But we know that something around, so 200 million, it's way too big. We know that 1 million, it's okay. And in fact, even somewhere between maybe 40 to 50 million should still be pretty reasonable. So the question is, can we drive this number down closer to this way so we don't actually do all the work? And if we do try all subsets, there's not a lot we can do. Okay, so we have to see, can we do something so that we don't have to do all subsets. Okay, now what is the CPU time limit they tell you? 2 seconds. So 2 seconds is not too small, but not too big. So you can't just do 200 million. Okay, so what is the idea? The idea is that instead of using the bit mask, so to try all subsets, what we did last time was try all bit mask from 0 all the way to 2 to the n minus 1. And then for each bit mask that represent a set, I test the set and so on. And if you do this, if you use a for loop that goes from 0 to 2 to the n minus 1, of course, it takes 2 to the n steps. But there's another way of doing it. So this is A. B, maybe you have to think, and this is actually kind of useful in many of these exhaustive search algorithms, it's to think, why is it that you have 2 to the n subsets? So I don't know when was the first time when somebody tell you that there are 2 to the n possible subsets, and then they maybe give you a proof. If you remember what is the reasoning of the proof that they're exactly 2 to the n subsets? Can anybody tell me, give me a quick proof why the total number of subsets is 2 to the n? Anyway, you have n objects. So if you're going to choose a subset, different subset, what do I do? For each object, I can choose the object or not. And that's 2 choices. So for each object, I can decide, do I choose it in my subset or do I not choose it? And once I make that decision, then I can kind of look at the next object. In every single object, I have 2 choices independent of what I have done before. And so basically, that's how you get the 2 to the n. Does that sound familiar? Any questions? Okay, so hopefully that sounds familiar. So why do I bring this up? If you look at the proof of why there are 2 to the n subsets, there's some kind of a sequential procedure that let's look at the first object, do I choose it or not? Okay, make a choice. Then you look at the next one, you make a choice, you look at it next. So you kind of choose objects one at a time. So this means that I can look at all possible subsets with some kind of recursive procedure. So you can kind of do a subset search, you will want to call it subset search. And maybe you have a Boolean array, okay, true or false, that tells you whether an object is chosen or not. And then you can just kind of choose things one at a time. Okay, so how would a subset search go? Okay, so move a little bit. Okay, so basically all you have to do is you have to say, well, you try subset k is equals to true, so that means you choose it, then you recurse. With one more element, and then you set it to false, so you don't choose it. And then you do recurse again. So basically, okay, hang on, I have to do something about my dog. Let me go and try to turn him off somehow. Okay, sorry about that. Okay, so You have this subset search, so you decide for each element k, either you choose it or you don't, and then you recurse. And then the base case here is if k is greater than or equal to n, that means you have run out of objects to make a choice for. Then, in this case, you have a subset, so then you have to do something about your subset, check subsets, I guess. And then, I guess, maybe here, in this problem, maybe you return an integer. Maybe you return an integer and check the subset. You can return the area if there's no conflict, or 0. And then here you would take, I don't know, when here you would have A1 is equal to this, A2 is equal to this, and then you would return the max of A1 and A2. Okay, so here you somehow have to do your check to see whether there are any pairs of rectangles that intersect with each other. And the way I've written it, this test here will probably be n squared, because I will just run a double loop to check all pairs. And then this is basically 2 to the n here, that recursively call things 2 to the n times. So at the end of the day, the way that I wrote it, it's exactly what I had before, 2 to the n times n squared, which is not very helpful. But before I move on to something further, is there any questions about how I write this search recursively? Okay, if there's no questions on how I write this recursively, then I want to show you where I can make things faster. So basically here, I will be adding rectangles, right? So I'll be rectangles here. And maybe I decide to add this rectangle, and maybe this one I decide not to add, and then maybe I decide to add this one, and then maybe I decide not to add this one, and so on. So maybe I consider this one, this one, this one, this one, this one, and then maybe some other rectangle later, etc. But once I decided to choose rectangles 2 and 4, there is actually, if I knew that 2 and 4 intersect, there's actually no reason for me to consider anything more, because it doesn't matter what are all the things I try, it will always have a conflict. So what do I mean by, so what's going on here? I've decided to choose 1, 2, and 4, and then I still have a lot of different, maybe let's say a bunch of other objects that I haven't decided whether I'm going to choose or not. But the 2 and 4 already conflicted, so I can go on and recursively try 2 to the whatever else here and do all this work, and none of that will matter because you already have a conflict. So instead of doing this check of whether there's a conflict at the very end, basically what I can do is here, when I decide to choose rectangle K, at this point I should check if rectangle K conflicts with previous chosen ones. Okay, and if there is, if it's conflict, then don't recurse here. Do not recurse if there's a conflict. And this is what is called pruning. Okay, so as soon as you realize that there's no possible way to continue the search to give a correct answer, you should get rid of that search as quickly as possible. And that, if you make sure you do that, that will make sure that you cut off a lot of things. So what does pruning mean? Right? So you can think of it this way. You start off initially with nothing chosen. Then at object one, either, so this is the empty set. Then maybe you have chosen object one, or you decided to choose nothing. And then object two, for each of those, you can decide to choose object two as well, or not choose object two, and maybe you choose object two and not choose object two, etc. So basically every node will have two paths coming out. Either you choose the next object or you don't choose the next object. Now imagine that 1 and 2, rectangle 1 and 2 already conflict. Then all of these nodes in this tree, you can keep exploring, but none of them will lead to a solution because you already have a conflict. And all this work that you're going to do, right? If there are 10 more objects, if there are 10 more objects that you have to choose after 1 and 2, then that's 2 to the 10. This size is 2 to the 10. If it's a more, then it's even worse. And as soon as you realize that 1 and 2 conflicts, you can say, I don't have to look at any of this anymore. So it's like if this is a tree, right? You know, in computer science, all trees are grown upside down. Then this just cut off that branch, and you never have to look at them again. And this is what is called pruning. And in general, if you can prune, you want to prune as early as possible. Okay. And with this, you will be able to get this running in time. Pruning, it's a little bit tricky in terms of analysis because you can never be sure. You can never be sure if pruning is going to be very effective or not. It's sometimes very hard to analyze exactly. It's more like a heuristic. Most of the time it will do well, but maybe there's some worst case that can make it unprunable. So for example, if I give you n rectangles, none of them are intersecting, then you wouldn't be able to do any pruning at all. But in most cases, you will be able to do some significant reduction of amount of work you have to do. So yeah, this pruning business it's a little bit more heuristic. It's hard to precisely nail down how much time you can save in all problems. Sometimes problems will allow you to have a more precise analysis, but not always. And all of this, it's made possible by the idea that I look at this process of selecting subsets one thing at a time. Okay, so I must break it down into a bunch of different steps, in this case, choosing one object at a time, so that I have a choice, I have a chance that after each step, I can try to get rid of things, I can prune. If I try to sort of look at everything at the same time, like in the first case, try all possible bitmaps here like this, it's hard for me to cut things off. Okay, but when I look at one object at a time, it is much easier for me to cut things off by considering what happens with each additional object. So, hang on, where is my code? Okay, so I think, so this is my code. So again, the main is not very exciting. It just basically solved a bunch of cases. I read in n the number of elements, the number of rectangles. If n is 0, then I just quit because n equals 0 means it's the last case. I have this rectangle class, structure, whatever you want to call it. Then I have a read function that reads in all the required data. It computes the area. I haven't really told you how to decide whether two rectangles intersect, but I'll get to that later. I pre-compute an array that stores whether two rectangle I and j intersect with this function. And then this is basically what I told you. I have a Boolean array that tells me which elements are in my subset, and then I search. So what does my search look like? So index. Okay, so my area. I see. My area actually is okay. So If I run out of things to choose, area is 0. Otherwise, I just call things recursively without setting chosen index to be true. So basically, I'm saying don't choose this current element. Okay, and then whatever that S returns is. Then I'm going to say, okay, what if I choose the current element? So then I look at all the previous elements. Either that element is not chosen. So make sure that it's not both, a previous element is not both chosen and collides with the current one that I want to choose. Okay, so if it collides with the current one and it has been chosen before, then I cannot choose it. So if I'm allowed to choose it, then I choose it. Then then I recursively call this plus the rectangle that I just chosen. So whatever it returns plus the area of the rectangle I chosen. And then I want to take the max of this against the existing S, which is the result of not choosing the current element. And when with recursive search, we usually want to make a choice. I recurse, then before, when I back out, it's usually a good idea to reset them. Okay, otherwise you can get all screwed up. So usually you want, whatever you set, you want to reset after you're done recursively. And that's pretty much it. The only other thing I haven't told you is how do I decide if two rectangles are colliding. Okay, so this is a little bit, maybe a little bit tricky. So because you can have rectangles that are colliding in a number of ways. Maybe they collide like this, maybe it could collide like this, and maybe different ways. And you might say, well, maybe what you have to do is to make sure that none of these 4 points, so you have each rectangle has 4 points, and you want to say, well, if I look at the rectangles, I want to make sure that the 4 points are not inside the other rectangle, right? Because here, these 2 points are inside this rectangle, so maybe you can say, that's good, that's intersecting. Here, this point is in this rectangle, this point is in the other rectangle, and so you might just try to look for that. But it turns out that this is insufficient because you could have a two rectangles like this, and none of the 4 points of each rectangle, it's actually sitting inside the other rectangle. So there are many ways you can do this, I guess. You can look at line intersection if you want. But anyway, the way that I decided to do it was first, I make sure that rectangle 1, it's always to the left or maybe to the same x-coordinate, starting x-coordinate as rectangle 2. So maybe it looks like this. Maybe it looks like this. And or maybe some other way. Maybe R1 is here and R2 is here. Who knows? But I'm always make sure that R1 is not to the right of R2. Okay. Basically, with these kind of problems, you probably will have a lot of cases to deal with, and by sort of normalizing this, I have fewer cases to deal with. And the way that I deal with this is basically if it's in the wrong order, I just call itself with the right order by flipping them. And then basically I look at R1 x plus w. So R1 x plus w is basically this point. If this is less than equal to R2x, that means that R1 and R2, R2's x value must start after R1's x value on the right edge. So then for sure, it doesn't matter where it is vertically, it cannot intersect. Otherwise, it must be the case that R1 is here and R2 starts before the end of R1 in terms of the x-coordinates. And then you have to say, well, is it this one? Is it this one? Or is it, this one? There are many different cases. But then basically the idea is that now I have to look at the y value. And it turns out that basically the only way that they cannot intersect once you have this is either one of them, it's either R1 is on top of R2 or the other way around. And this basically checks that. Okay, so this is a little bit, the details are maybe a little bit more messy for checking if two rectangles intersect, but it's definitely a good exercise about geometry, because the problem is fairly simple, trying to see if two rectangles intersect, but it shows you all the different traps that you can fall into if you're not careful. Like this particular kind of intersection, most people when they're trying this for the first time will miss this kind of intersection. They might only test for intersections where one of the points in one rectangle it's inside the other rectangle, and then you'll miss this kind. Anyway, so that's this problem. Any questions or comments? Okay. Okay, so now let's look at this paintings problem. Okay, so painting. So there's n vertical strips of distinct colors, and you want to choose a color for each vertical strip. She always begins painting her vertical strips on the left side of the canvas and proceeds to the right side. So always goes from left to right. There are certain pairs of colors that Kathleen doesn't like seeing next to each other. If two such colors are adjacent in a painting, she considers this painting to be hideous. Furthermore, there are colors Kathleen prefers over the other colors, so when painting, she always selects her most preferred unused color that does not make the painting as created so far hideous, and that allows her to complete a non-hideous painting. Can you help Kathleen find her favorite painting? Okay, first there are T cases up to 5. Each case there are n colors up to 12. And Kathleen wants her painting to have, on the second line, there are n colors ordered in strictly decreasing order of preference. Each color is a string between 1 to 20 lowercase letters. The third line contains an M, indicating the number of pairs of colors that follow. Each of these next M line contain 2 colors that Kathleen does not like seeing next to each other. No pair of colors will appear in more than one line. Then you are supposed to produce the total number of paintings that you can make that are not hideous, and then followed by the painting that is her favorite. You're guaranteed that there's always at least one arrangement that works, and the maximum number of paintings that works is at most 100,000. Okay, so what does it say? For example, here there's 3 colors. Okay, there's 3 colors. She likes green the most, and then red and blue, but she also doesn't want red and blue to appear next to each other. So if you just look at this, green, red, and blue would be her favorite ordering, but it doesn't work because red and blue appears next to each other. So with 3 things, there are really only 6 orderings, 3 factorial, right? BRG, BGR, RBG, RGB. Those are the 6 possible orderings. Red and blue cannot occur together, so red and blue cannot occur together. Red and blue cannot occur together. And now you're left with these 2. So only 2 good ones. And then you want the red first, because red is her favorite color compared to blue. So this is this answer, and the 2 comes from these 2 cases. So again, as we said, this, if you're doing some sort of search, you should ask yourself, what kind of things are you searching for? And in this case, because you have n things, and each one can only be used once, and it's an ordering. This is a permutation of n things, right? Now, how bad is n things, right? So what's n things? So it's n factorial, of course. And n is up to 12. So, can you try all possible permutations? We talked about using this mixed permutation function last time. And what's 12 factorial? So 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8 times 9 times 10 plus times 12 is 479 million. Okay, that's way too big. 10 factorial is usually okay. 10 factorial is 3.6 million. That's not much. If somebody tells you to look at all the possible permutation of 10 things, it's absolutely doable, assuming that you're not doing too much per permutation. 11, it's a little bit pushing it. 11 is about 40 million. So that depends on how much you're doing for each permutation. If you're not doing a lot, that's fine. If you're doing a little bit, even a little bit of work, it might be a bit tight. But 12 is definitely out of the question. Now, you do have one thing that it's good. They tell you that even though there are lots of permutations, they tell you that the number that will work is at most 100,000. There are not that many that will work. And what that means is that the pairs of constraints that they give you, there has to be enough constraints that make sure that you cannot have too many. So what we have to do then is we have to say, instead of saying generate all n factorial permutations one by one and check if they are okay, we have to utilize a similar strategy where we try to select things one by one, and we kind of prune things as soon as possible. Once we realize that it's not going to work, we want to prune things. So let's look at this again. The n factorial permutations. So n factorial permutation, of course, is 1 times 2 times 3 times 4 up to n. And again, I don't know when you learn this fact that there are n factorial permutations, and n factorial is this sequence of numbers in a product. When do you learn that the number of permutations is n factorial? And what is the proof? So you have n objects, you have n positions, and what you learn, I hope, is that the first position you can choose n different things. Any of the n objects can go into the first position, right? Because nothing has been used yet. But once the first one has been fixed, the only thing that you can use are everything except the first one. So there are now n-1 choices. And similarly, the next one, you can choose any of the remaining n-2 elements, but not the 2 that have been chosen already, and so on. And those are the choices you have for each position, and that's how you get your n factorial number of permutations. Okay, and again, the proof in this case has some kind of a steps to it, right? So first step, you choose the first position, choose the next position. So you're choosing objects from one at a time, right? Choosing the objects one at a time from left to right, if you want to call it that way. So we're going to do exactly the same idea. We're going to choose a color here. We're going to choose a color here. And every color that we choose must be one of the remaining colors. that have not been used. But where are we going to prune? Well, when you put a color down here, the only possible problem is that if you look backwards to the last one that you put down, there's a conflict. Okay, in this case, you're not allowed to put conflict colors in adjacent order, so an adjacent position. So when you put this one down, the only thing you have to worry about is, did it conflict with the one before? You don't have to worry about that, would it conflict with the one after, because you haven't made that choice yet. And it will be taken care of when you make this choice later. And as soon as you discover a conflict, you can stop. And by doing that, basically you would be able to prune for the same reason as before. You could, if you say, let's say here, that you discover that you cannot continue, then you're basically saving yourself looking at all the permutations of the remaining objects. So then the next question is, how do you write permutation generation in one object at a time? And it's going to be recursive again. Most of these things are recursive. So I'm just going to jump straight to the code here. So again, main doesn't really do much. It just loops through the cases. Okay, so what's going on? So I read in the number of elements. C is an array of a vector of strings. The fact that they use strings instead of as colors instead of numbers doesn't really make the problem conceptually harder, but it makes things a little bit trickier to write because you have to deal with changing between numbers and strings and vice versa. But anyway, C is it's a vector of string. Then I read in all of these strings, and also I have a Boolean two-dimensional array called bad. And if I have I1 and I2, and this is true, that means that color I1 and color I2 cannot be next to each other. If it's false, it means that you don't care if they're put next to each other. So then I read all the pairs of forbidden colors. I read in the two strings. Then I basically look up the index. I have this array of colors that are strings. I did a linear search to figure out where they are. So this is linear search. Why do I use linear search? Because there are only 12. There are only 12 colors. So it doesn't make sense for me to do something elaborate like binary search or whatever. I might as well just do my linear search. Okay, so, and when you tell me that there's a pair that cannot appear together, I will set the entry to be bad. Okay, then I'm going to look at all permutations. Now, this is a function that you may not know. IOTA basically fills an array or a vector or any kind of container, starting with this first element is whatever you say, and then every element is one bigger than the previous. So basically, this gives me up to n minus 1. Okay, basically, it's the first permutation. And then forget about this first thing for now. And then I have this recursive function that takes my permutation so far and the object that I'm deciding, the position that I'm deciding. Remember that I'm going to decide the first position, which of the n objects do I choose? The next position, which of the remaining objects do I choose, and so on. So let's go quickly to the recursive function. So recursive function for generating permutations always look kind of like this. You have some array or vector that stores the permutation so far, and an index that says which position you are selecting so far. If the index is greater than or equal to the number of elements, then you hit the base case, you got a permutation, then you do something with the permutation, which we'll come back to later. Otherwise, it always goes like this. So what does it look like? Oops, what just happened? I pressed the wrong button on my pen. Okay, so you have an array that represent a permutation, and you have an index here. And when the index is here, it means that you have already selected something for the first part. And then maybe here you just have 0, 1, 5, 6, 8. Okay, it may not even be in this order, but these are the remaining things that have not been chosen. Okay, so now what you're going to do is you're going to say, well, this position can be any one of these 5 things. So I'm going to loop any one of these 5 things. I'm going to loop at my I from index to the end. Whichever I I'm pointing to, I'm going to swap that into this position. So I'm going to put 5 here, put 0 here. And that means I decided to choose 5 for this position. Okay, we'll ignore this other part. And then I recurse, which basically says, now I fixed this position, I'm going to recurse. So give me a permutation of the rest of this stuff. And then when I come back from the recursion, I always clean up by swapping back to restore things. Okay, this is also important. So that's the basic structure of generating all permutations recursively. But I'm not doing all permutations. I'm trying to do some branching, cutoff, pruning. So what do I do? Well, okay, so I'm going to check. After I've swapped in the 5 here, I'm going to check, am I good? So why am I good? It could be that it could be that I'm at the first position, in which case there's nothing I have chosen before, so there's no way to conflict. So that's one way. Or what is in index -1? So what is in index? So here. And what is in index -1? These two is not a conflict. So either I have nothing to conflict because I'm the first one, or I look at the one before me and I look at my table and say, am I one of the pairs that are conflicting? If I am not conflicting or I'm the first one, then I'm good. If I'm good, then I'm allowed to proceed. Okay, then I'm allowed to proceed. Otherwise, I'm not allowed to proceed. I just prune. So I don't recurse if I'm not good. And this is where I manage to save time to cut off the search. Okay, there are a few other things that maybe I say now. So what is this recursive function returning? The recursive function is returning int, which is counting how many permutations are good. When I get to the base case, it means I found one that is good. So I return 1. Otherwise, if I'm not the base case, I start with 0. Every time I recurse, whatever it returns, I add it up, and then I return the total. Okay, that's kind of that's how I keep track of how many there are. And then finally, I have to produce the permutation that is the best one meaning that it has the smallest index at the beginning and so on, because the input is given to me in decreasing order of preference. And what I do is I basically compare the permutation that I'm constructing against some permutation that I have saved as the best one. And I use something called lexicographical compare, which is basically means that the first position is small as possible, and if there's tie, break tie with the next position, and so on. And so if I somehow find one that is better than what I've saved, then I just copy it. And then I also have this first equals is a global variable that basically says, have I even, maybe the first time I run this, maybe it, how should I say, if I've never discovered a permutation that works before, then this is meaningless because I've never saved it. So in that case, I don't even bother comparing it. If I've never seen a permutation that works before I just copy it. That's it. And then I set first to false. So from this point on, it will always compare with what I have found so far. Okay, so this is a little bit, maybe a little bit more messy than just straight trying all permutations. Okay, but this part, anyway, it's a very standard generate all permutations recursively code. Okay. Any questions? So you can see probably that I'm starting to give you a kind of a pattern that I do things recursively, but I try to generate things one at a time. And this is useful in that it is a good way to allow you to prune early. Another way to think about it is instead of checking everything at the end, right? So you generate all the permutation and check if it's okay. I'm spreading out the check everywhere, right? Each step I'm spreading out the thing that I just picked violate whatever I have to satisfy, and I'm kind of spreading out the check at each step as opposed to doing it all at the end. And sometimes that allows you to determine if something can be cut off earlier. Okay, any questions before I move on to the last one? Okay, committee assignments. Matthew is the only one that tried it here, but Matthew is not here, so okay, that means I cannot pick on him and see what he did. Okay, you're the chair of a large department, and as such, it's your job to assign department members to committees. Everyone has to be on exactly one committee, but some department members don't get along and cannot be assigned to the same committee. Of course, you want to have as few committees as possible since it's hard to make up jobs for committees you don't really need. So what you need is a program that figures out how many committees are needed so that no mutually hostile department members are placed on the same committee. Okay, input consists of up to 50 department descriptions, starts with the positive integers up to 15, and a non-negative integers m, which is up to n, choose 2 basically. The value of n indicates the number of people in the department. M tells you how many pairs don't get along, followed by m lines, which are the names of 2 different people who don't get along. And then name is a unique sequence of 20 letters. Each person has a unique name, and of input is part by a pair of zeros. For each department description, print out a line giving the minimum number of committees needed to keep mutually hostile department members on different committees. Okay, so let's look at this. First case, 5 people. There are no hostile pairs, so you can actually just put everybody in the same group. Okay, so that's easy. You have 5 people again, but this time you have 2 pairs that cannot go together. So Alice and Wally cannot go together. Wally and Dilbert cannot go together. But, you know, there are 5 people, there are only 3 names mentioned. So the other 2 actually doesn't matter. I'll just call them 4 and 5. These 2 other people, they can go anywhere. So actually, once you decide what to do with these 3, you can just stick them anywhere to the existing groups. It doesn't matter. So you can actually just ignore these guys. So WA, and so you can definitely not put all 3 of them together. But if you put Wally on one and Alice and Dilbert on the other, that's okay. And then over here is a similar idea. You have Greg and Don, who cannot go together. Greg and Bill, who cannot go together. Don and Bill cannot go together. The other 2 doesn't matter. Again, they can be thrown anywhere. So in this case, you can't put any of these people together, so they all have to sit in their own group. Okay, so that's the question. Now, again, we have to think about what do we actually mean? What am I actually searching for, right? I'm searching for a way to assign people into committees. But how do I represent this committee? that's a little bit trickier because in this case, it's not a subset of people. You have a bunch of subsets of people, but then these subsets cannot really overlap and it has to cover everything. It's not permutations either. So what is it? It's a little bit tricky to see. Anybody have any idea how you can represent an assignment? Any idea of how, if I say I want to know what is the assignment of people to committees, how would you even store this? Okay, so I have 15 people. Well, it doesn't matter if it's 15. Let's say 1, 2, 3, 4, 5. Yeah, 5 people. These input have only 5 people. So how do I represent which committees they are in? One way that I can represent is it's just give everybody a label, right? So maybe I say 1, 1, 2, 3, 2. And what that means is that people 1 and 2 are in a committee label 1. People 3 and 5, they're in the same committee. And person 4, it's in yet another committee. So that's one way to represent committees. Okay. And if that's what you're thinking, if that's what you're going to do, then the answer, the actual number of committees that are used, it's basically the maximum of all the labels. Okay. And you want to choose a set of labels so that the max is minimized. And of course, you want to make sure that none of these constraints are violated. So you might say, well, okay, let's try. Maybe the first label to try, of course, is 1, 1, 1, 1, 1. Put everybody in the same committee. Maybe that doesn't work. Then what do you try next? Right? Maybe you try 2, 3, 4, and so on. So, and that one way to think about it is, at some point, you have decided that the previous people have a certain number of committees, whatever the label is. At this point, what do you do? Well, basically for this person, you can do one of 4 things. You can try putting him on any of the existing committees, right? You can try putting on any of the existing committees or create a new one just for him. You can always start a new one. So every step, the number of choices you have, it's going to be any one of the existing committees or start a new one. So the first position, there's always one choice because, well, it doesn't matter what you label that committee, the first person always goes in a new committee. The second person can either go into the previous committee or start a new one. The third one can go into the previous 2 committees or start a new one. So there's 3 choices. The next one has 4 choices, 5 choices, and so on. And you can see, hopefully, that this is basically n factorial committee choices. Okay. Now, of course, some of these doesn't make sense. So for example, maybe you decide that this is, maybe you try putting 2. And then you realize that this 2, well, it conflicts with one of these people, that they are not allowed to be on the same committee. Then you cut that off and you try a different one. And that's basically all you have to do. And I don't want to say too much more because it's pretty much the same drill as before. So I'll just dive into the code. So if I dive into the code, then again, there's a small problem, small mess, because of the fact that you're given names and some of the names don't even appear in the, so, but anyway, I read in the input parameters n and m, n people, m pairs. For each pairs, I read in the names. I have some way to convert the names to an index. I have an array that says whether two people can be together or not. I have a label, and then I have this search algorithm. Again, it's going to be recursive. So what does my search do? This is a little bit trickier. So I have a label array that I'm keeping track of. Persist index is which person I'm trying to assign the index label to. And then num is the maximum number of, it's the number of committees I have used so far. And the base case basically this, if I run out of people to choose, to assign, then the maximum number of committees I've chosen so far is exactly the answer. Then basically for now I have to decide what does this person go, which label do I give him to? Is he going to be 0, 1, 2 all the way up to none? Okay, if I've used four committees before, that means that my committee labels are 0, 1, 2, 3. And going to 4 means that I open a new committee. So I do all of that. I try everyone. I'll skip this one for now. Skip it. So for each label that I can try to assign, I assign. Then I assume that it's okay to assign this label, but I don't know, so I'm going to check. For every person that I've chosen, every person that I've assigned before, make sure that either that person, it's not conflicting, in which case I don't have to check anything, or if it's conflicting, I better make sure that the labels are different. Okay, so either the person doesn't exist on my conflicting list, or they have different labels. I want to make sure that every person is okay. So if every person is okay, then I recursively search by basically going to the next person, and then this basically tells me whether what is the maximum number of committees I've used so far, and this will basically increase by 1 if I am at the last point, meaning I open a new committee. Okay, and then I always clean up and assign it back to 0. In this case, I don't think it's absolutely necessary, but it's good practice, just in case. And then I always compute the minimum, right? Because I'm trying to minimize the number of committees used. So I'm always keeping track of a best possible answer so far. I can always use n committees by making sure that everybody has his own committee. And then whatever comes back, I always try to take the minimum so far. Okay, so that's the gist of it. And if you don't have this line, it turns out that it will run too long. So what does this line do? This line basically says, okay, so I'm trying different labels, right? I'm trying different labels, and answer, it's going to keep the minimum number I found so far. So maybe after running through this a few times, maybe I know that answer is 4 so far. Okay, so far I have managed to find that there's at least one way to use only 4 committees to finish the job. So in this loop, if I'm trying to assign, okay, label of this person to be 0, 1, 2, 3, and then 4, well, if I try to assign label 4, then immediately I know that I'm using at least 5 committees, because 0, 1, 2, 3, 4 is 5. And if I already know that the answer is no bigger than 4, then there's no reason for me to try to assign 4, 5, 6, and so on. Because no matter what I do, the answer is going to be worse. So this is another early cut. So there's 2 early cutoffs here. This early cutoff basically says that if I know that the answer is going to be a certain number, then there's no point of me trying to use more committees than the best known answer so far, because it's not going to be any use. The answer is always going to be worse. And then the other pruning here is that when I find when I try to assign somebody to the committee, if that person is conflicting with the previously chosen assignment, then I'm just going to quit right away and not recurse. Okay, so this one is probably the most complex one out of the 4 that I chose. And as usual, all of these ones are on my GitHub, so if you want to refer to it. I would say that you should definitely try B and C. Okay, those are definitely something that everybody, if you want to be well-versed in competitive programming, you should have a good handle on. A is a slightly different problem, right? It's a breadth first search, but still breadth first search is also fairly standard in graph algorithms, so you should also look at it and try it. B is a little bit of a different animal compared to the other one. It's B and C and D are all in a similar way in terms of the code. It's very similar approach, but I wanted to show you sort of 3 different things that you're searching for, right? One is a subset, one is a permutation, and then this last one is, I guess, neither one of the standard combinatorial things that you learn. But in any case, it's still the idea that you have to make a bunch of choices, one at a time, for each. So then you write a recursive function that basically make the first choice and make the remaining choices. And every time you make a choice, you check to see if the choice still makes sense. And if not, don't recurse. That's really the main theme in this set of problems, B, C, and D here. Okay. So I guess for this week, that's pretty much all I have. Any questions, comments, or requests for next week? Okay. No requests? Okay. So let me stop the recording.